Welcome back. Welcome to General Chemistry. We're going to be talking about waves, the speed of the wave, the wavelength, and other characteristics that allow us to understand better how waves behave. So the first thing I would like to show here in this picture is that very common phenomena in the Northwest is, of course, lightning strikes. And here we have a nice picture of lightning striking down, and we know that we will see it and we will also hear it. And we also know that we first see it and then we hear it. And in fact, the more further away that we are, the more the difference between the time of arrival for the light to come relative to the sound, that would be an indication of how far the lightning is happening. So if you are really close, you will hear it and see it at the same time. That's not really very good. Sound is a different kind of wave than light. Light travels at very fast speed. It will be about 300,000 kilometers per second, which is about 200,000 miles per second. And sound goes about 340 meters per second. So they are very different waves, therefore they travel at different speeds. So let me talk a little bit about some of the characteristics of waves. The first one that I would like to mention is amplitude. Amplitude refers to how big the wave is. That would be the height of the wave. And you can measure the amplitude by looking at the distance from the center of the wave, let's say the mean, the average value, to one of the highest or lowest points that we call the crest or throat of the wave. I have a picture here that I'm going to show you in a minute that we will talk about that. And then the other one, of course, is the wavelength, which, as the name implies, we're talking about the length of the wave, right? So we use Greek letters like lambda to determine what is the wavelength of the wave, and that would be measuring the difference between two similar points. That would be the distance that you will have between, let's say, one crest to another, the next crest, the next crest. So this distance is going to be characteristic of a particular wave, and something that you have to know is that the same distance that you have from crest to crest, you have from throat to the next throat, right? Or you can have it between the distance between two alternative notes, like in this case I can show you what I am talking about. The distance between this point over here and this point over here, which are alternative but they are equivalent. You see the wave is going down here and it's also going down here, so these 2 points are equivalent, and the distance between these 2 points is what we call the wavelength, right? So the question here is, how can I relate the wavelength to the speed of the wave? If the wave is traveling in that direction, let's say, how can I know what the speed is? Well, one way of looking at this is, let's say that you have an observer standing over here on the right hand side here. Let's say this is the eye of an observer here. I'm trying to make a little drawing of an eye here. And okay, that's the nose, mouth, and so on. Not that bad using my mouse here. Anyways, so if you're looking at the observer here and the observer is fixing into this point, he can measure the time that takes for the following alternative point in this curve here to arrive here, right? And that time is what we call the period of the wave. And there are many different letters that we use for that, right? So for instance, if we have that we get one wavelength per second, you will say that the frequency of that wave is 1 second, right? So you can look at the speed here by looking at the wavelength divided by the time it takes here, because remember that when you have velocity or speed, you have the ratio between distance d. In this case, of course, we're talking about lambda. The distance is going to be one wavelength, and the time it takes, and in this case the time is going to be the period or frequency related here. So by knowing what is the period here, and let's say you have 1 second, then the wavelength here is going to give you the ratio here. Now you can see here how frequency, that we are going to be using the letter nu for frequency. In some books we use the letter F for frequency. This is going to be the inverse of the period. So for instance, if I have that the wavelength takes 1 second to go across, that means that you have 1 cycle per second, right? So the letter here for this one would be related to how many cycles do you have. So you have 10 cycles per second, you have 20 cycles per second, you have 20 cycles per second. And that unit, in fact, has a name. We call it the hertz. So hertz is the per second, how many cycles per second have. So if you have a 100 hertz, that means that you have 100 cycles per second. So if you put the hertz here, you will see that the speed of the wave, I'm going to call that the velocity of the wave using v, is going to be equal to the wavelength times the frequency. And I'm going to put nu here, right? So by multiplying this, the wavelength could be meters, for instance, and the frequency is going to be per second, so you will have meters per second, which are the units of velocity or speed. So this is how we are going to be working in class, so keep this in mind. I hope you enjoyed this video, and I will see you pretty soon.